Hey there, math fans. Dr. Andy Loves. I'm going to talk about the Summer 25 Exam 2. As I always do, I'll do a short video for each page. For my students, I'll go through the solutions. Please also check my written solutions, ask me questions. For anybody else watching this, I want to also show you why this is interesting. I try for every question to have it be of some applicable interest. So this first question had to do with acceleration in studying a curve. I gave a curve in 3D that was given by x equals cosine, y equals sine, and z was given by this quadratic. So part of what we were learning at that time was how to study that motion. So if you were to plot it, it's like that red dot moving around that you can see there. If I was to label all those and connect them, it's this thing. Now, hopefully you've learned at this point, you could even visualize it a little bit. Like you could eliminate the parameter. You could say x squared plus y squared is 1. And that gives you this cylinder. So every point is on this cylinder. So those are ways that we've learned to analyze it a little bit. Okay, that's a side topic. So back when we were talking about this, we said, well, what about the acceleration? When is it speeding up the most? What can we say? And we learned to find some vectors. So we found the derivative vector, which was this thing. Let me slow this down a little bit. And it sometimes gets longer or shorter. You can see it's slowing down. It's getting shorter. Here's the acceleration, which is like the way you're being pulled, we sometimes think about. And we talked about how sometimes you're slowing down, sometimes you're speeding up, like there. And sorry, it's going too fast. I'll go a little bit slower. So there you go. We are slowing down, speeding up. There's an interesting moment here, and at that moment, the acceleration and the velocity are perpendicular. We measured that back when we were doing this by talking about the unit tangent and the unit normal. Here, I'll zoom in. The orange being the unit normal. And that is the one time it points that way. So we talked about how acceleration sometimes pulls you forward or backward, speeds you up or slows you down, and turns you. Okay. So I'll leave that going. But we learned a way to separate these pieces. So we learned that the tangential component of acceleration, basically the amount of the acceleration that's in the direction we're going, we can compute, and it's given by this formula, r prime of t dotted with r double prime of t all over the magnitude of r prime of t. And we also had the normal component, which we can compute this way. So in terms of doing the question, it was an opportunity to compute. You didn't need to compute the second one, you had to compute the first, and you didn't even have to compute it all out. You had to find when it was equal to 0. So my students hopefully would know, and most students got this right. The vast majority got this right. So this is one of the easier questions on the exam. If you missed it, you missed it. It's not meant to be a criticism, but this is something we can handle. And we talked about this. We knew this was coming. So hopefully my students knew to immediately take these derivatives. Cosine, negative sine, and 2. And then we want the dot product of these two things, which is the top, to be equal to 0. Now I talked about this when we were reviewing in class. You know, if you're setting this equal to 0, you're trying to find when it's equal to 0, you don't even need to compute the denominator. Because the only way that fraction is going to be 0 is if the numerator is 0. And a nice thing happens. So we talked a lot about how you have to kind of look for simplifying. So if I multiply the first two together, you get a positive because of the two negatives. You multiply these two together. That's why we can do this. Normally you would need like a solver to find this moment. Plus 2 times this. And we want to know when that is equal to 0. Those cancel. So you end up getting that t has to be 2. And then we're done. The question was, what is the location? And so it was cosine of 2, sine of 2. And if you plug into it, it's 4 minus 8, so it's negative 4. That is that moment when they're perpendicular, when the direction you're going and the acceleration are perpendicular. That is the moment when you're like going the slowest here in our little model. So here, I'll show it here. So here is t equals 0, and then we're slowing down. We're right here at t equals 2. Now for my students, I know that a lot of that was kind of challenging and new, but I hope that you can see that this would be a valuable, these are valuable tools if you were measuring motion. These are the sorts of vectors that might appear in a physics course. Okay, let's move on to the next question. And I think my hope is that, sorry that I covered that up for a moment. I think that's a question you could have been prepared for, straight calculation. Okay, the next one says compute the partial derivatives. Now, I have been discovering that part of the issue is, even though there's some of this in the homework, I think some students just have forgotten their 124. So I'm going to make an even bigger emphasis the next time I teach it, but we knew this was coming. And so, please ask me if you find a topic like this that you're stuck on. Now, this particular surface, what you're studying, is called the Plucker conoid. I picked something that's real. It's kind of interesting to study. Oops, I realize I'm off the page here. So again, I'm sure my students are going to be frustrated that I'm showing these visuals. I'd just like to show you why it might be interesting. It looks like a pinched piece of paper. You've probably seen things like that before. I was trying to think of the analogy, but like a pinched bed sheet or something that you get. Supposedly this has some properties. People have studied this, used it for a few things. So I didn't pick something totally random like I normally would have done. I'm trying to pick things that have interest. I looked something up, but it's defined implicitly. So if you wanted to deal with slopes on there, you would need to be able to compute the partial derivatives. So here, this notation meant x was my input and z was my output. So it meant we were thinking of the function like this. And so I find that, like I said, it's really a Math 124 review. You could have done this. You could have solved for z and completely ignored doing the implicit stuff, which would have been perfectly fine. You would have used the quotient rule. You would have gotten it. But I'd like to review this here. So you have to think about, this is a function. It's like you have a function there. Sometimes I tell students, what if that was sine? How would you take the derivative here? Well, you'd have to use the product rule. But I'm not going to call it sine. I don't know what it is. I just know it's a function of x. And usually we don't put the x in there. That's something we should already know. That's what we were doing back in Math 124. So I'm going to take the derivative with respect to x, treating x and z as the variables. So this, and this. Okay, so on the right, we're just going to get 10y. And on the left, we're going to do the product rule. This is the first, this is the second. It's a product, and there's a variable on each side. So it's first times the derivative of the second, which is 2x. Because x is our only variable there. And then the second times the derivative of the first. The derivative of the first is dz dx. That's the part where the implicit comes into play. And at this moment, you could solve for dz dx. That's perfectly fine. dz dx is going to be 10y minus 2xz. This is an important, valuable thing that we can do this implicit. Or you could have just plugged in directly, because I already said the value was 133. So you could have done it right here. 1, 3. This was 1. This was 3. This was 3. So you get 6 plus, I think this was altogether 10 dz dx equals 30. So you got 10 dz dx is 24, and you got dz dx is 2.4. Okay, most students did pretty well on that. That's the slope in the x direction. So here's this point right here that I gave. Here is the line in the x direction. How did I give that line? Well, I used the fact that the slope was 2.4. I made a vector that has slope 2.4 in the x direction, and I got that tangent. Interestingly, this is, I didn't realize this till I showed this. This has an infinite number of lines that are completely contained on it, called ruling lines. I didn't realize that there were equations like this that had an infinite number of ruling lines. I thought that wasn't possible. So just in making this visual, I encountered something I've never seen before. So that's why I tell my students, you keep exploring when it comes to these things. There's mathematical interest, and then there's intrinsic interest. I hope you found that interesting. I'm going to move on to page 2. All right.